Welcome to Study Loop.
All right, for this problem, we want to find the maximum acceleration when a 60% reduction in force on A is applied. So first we want to find the angle theta, which is arctangent of 120 divided by 50, which are the two distances of the bar here and here. And so we find that theta equals 67.4 degrees. So now we can take the moment about O, and we want to take the moment here since it'll let us find NA. And taking the moment here means we don't have to include either of these forces, OX or OY. So that simplifies our calculations a lot. And we also know that M1 is 5/17 times M, and M2 is 12/17 because the bar is uniformly distributed mass. So of the 50 millimeters here and the 120 millimeters here, that's a total of 170 millimeters in length. And so 50/170 is 5/17 times the mass of the whole bar, and the same thing for M2. So now we plug in these values and we solve for NA, which we can do by adding this to the other side, this term here, dividing by G, and we'll find that NA equals 0.427. Or my mistake, we actually don't divide by G. We're going to leave it as 0.427 times mg. So that's the force being applied at this button here at A. And so now the problem tells us that we've got to reduce NA and take this system out of equilibrium. So we're going to have a 60% reduction like the problem specifies. So all we got to do now is multiply NA that we got here by 0.4. That's going to make this 0.1708 mg. So now that we reduced NA, the system is no longer in equilibrium. It's going to start moving, and we need to find the acceleration of it once it starts moving. So once again, we take a moment about O, and we get the same equation as before. The only difference is now NA is a different value. It's smaller, of course, because we just multiplied it by 0.4. We reduced it. And it's no longer in equilibrium, so it doesn't equal 0. It's equal to MA times D, where D is 25 sine theta. And the way we get that is that this bar is 50 in length. We want the vertical length. So we take half of the bar, and sine theta calculates our vertical length. So that's the distance from O to the center of mass where we want to calculate. And so once again, we just have to solve, except this time we're solving for A. We plug in the same values for M1, M2, and theta, and we get A, the acceleration, is equal to 1.443 times G. And so that's the acceleration when we take this out of equilibrium by reducing it.